To build on where we left off in the last video, we said that heat is equal to enthalpy change under isobaric conditions. So when the change in pressure of a system is zero, heat and enthalpy change become the same, have the same value. We're going to restate the first law of thermodynamics again. Change in internal energy is heat plus work. Or if we take work to the other side, we could say that heat equals the change in internal energy minus work. And remember, when we say work, we mean expansion work. So work is minus the pressure times the change in volume. So this implies that heat is change in internal energy minus work, but positive work is minus, so minus work must be plus P delta V. Okay. Let's divide through by delta T. So we're going to divide by delta T. So we've got Q over delta T is change in internal energy over delta T, change in temperature, plus P delta V over delta T. So we just divide through this equation by delta T and we get this equation. I'm interested in making this disappear, so I would like this to equal 0. How do I do that? Well, I have to make either delta T equal 0, and that won't be good because that will make these 0 also. So it makes more sense to make delta V equal 0. Well, delta V equals 0 under isobaric conditions. So in a previous video, we saw the vocab isobaric conditions means that delta V is 0. If delta V is 0, this whole system, this whole part of the equation equals 0 also. So I'm left with this expression here. So heat over delta T is the change in internal energy over delta T. That whole thing is a constant volume. Constant volume because the change is 0. If the change in volume is 0, we're saying it's a constant. This is known as capital CV, and capital CV, this thing here is the heat capacity. At constant volume. Okay. So the ratio of the change in internal energy with temperature change at constant volume is the heat capacity at constant volume. The heat capacity at constant volume is mass times by another C at constant volume. Notice this is an uppercase C, a capital C. This is lowercase. This could be mass. And this is something called specific heat. So heat capacity is equal to the product of mass times specific heat. In general, we have an equation: heat is equal to heat capacity times by a change in temperature. Or we could say in general heat is equal to mass by specific heat change in temperature. Remember, if we impose isobaric conditions, we can link this with enthalpy change if we have isobaric conditions. So typically in the lab, we'll measure a temperature change and we'll link it to heat. So you can't measure heat, but you can link it to something you can measure, so we can measure temperature change with a thermometer. You can think of heat capacity as the obstacle faced by energy as it is transferred between materials. So for example, if heat has to, or if energy has to go from left to right, and I'm in the way, and I capture some of the energy, and I'm in this room will have a high heat capacity. Heat capacity is all to do with obstacle to energy transmission or storage of energy, preventing it from being transmitted somehow by some mechanism. So that's heat capacity. The last thing I would like to do in this video is to briefly say how heat travels. There's a lot of misconceptions about how heat travels. Some people say heat flows. Heat doesn't flow. So those people are incorrect. Let's say this is a hot cup of coffee. Hot cup of coffee. And let's say I have a chocolate bar right above my hot cup of coffee. You might notice in the real world that the chocolate bar looks like it's melting. So somehow heat is going from the hot coffee into the chocolate bar. It's causing the chocolate bar to melt. But there's no flow of an object called heat. Even when scientists say heat flows, they don't really mean it. It's an unfortunate way that people speak. They don't really mean it flows. We know the kinetic energy, which is the energy of motion. Anything that moves has kinetic energy. Kinetic energy is the mass of an object multiplied by its square velocity over the number 2. Okay, this equation is worth remembering. Kinetic energy, the energy of motion, is the mass of an object, its square velocity over the number 2. Now if you take the average kinetic energy, well, that is related to the average square velocity, which is proportional to the average temperature in Kelvin. So, as the temperature of an object increases, it's because, on average, the square velocity of its pieces increases. So, for example, if this marker is moving with a velocity, I can increase the temperature, or I can slow it down. So I'm getting dizzy watching this thing. So this is velocity of a cool object, and I can increase the temperature of the object, or I can cool it down again. So if you imagine the hot coffee, the molecules inside the coffee are moving with a high kinetic energy. If you imagine the molecules in the chocolate bar, which is cooler than the coffee, are moving with slower velocity, so a lower energy. Now you imagine that there's some steam coming off the coffee. So my hand is the chocolate bar, moving kind of slowly. Now imagine that the marker is the quick moving water molecules in the coffee. So as the coffee starts to evaporate or produce steam, the steam is now going to hit my hand. My quickly moving marker is now going to strike my slowly moving hand. And some of it's going to make my hand move. Well, now I'm increasing the temperature of the chocolate. So it's mechanical. Heat doesn't flow. There's a mechanical exchange of energy. The fast-moving coffee causes the chocolate to speed up by hitting it. If you speed up, if your molecules move quicker, if they have more energy, they move quicker. If they move quicker, the temperature increases. So via mechanical exchange of energy, the chocolate temperature increases, and we observe the chocolate melting. So again, nothing flows. They're just fast-moving molecules that make slower-moving molecules move quicker. It depends on there being molecules in between to do the moving quicker. If you take all the molecules away, there's no change in heat.